Hey, what's up, guys? Let's move on with the lectures. And today we'll discuss a short topic, but a very important topic, and it's called infinite series. These series are normally derived from from a basic parent series called the Fourier series, which is a little more difficult to discuss, but we'll surely discuss about it. So first of all, we should know that some basic functions are always can be expanded into a series, and that is given by the Fourier law, uh, which we'll discuss obviously, but not so extensively, but as a normal interesting fact. So let's see what is this expansion of sin x, which is a function or a trigonometric function of x. It is x to the power 1 upon 1 factorial, or just x upon 1 factorial, minus x cube upon 3 factorial, plus x to the power 5 factorial, plus x to the power 5 upon 5 factorial, and so on. But first of all, you should know that if you don't know the meaning of factorial, I have given it here. Well, the factorial is like if you have 3 factorial, then it means 1 into 2 into 3. Like if you have x factorial, that means that we need to multiply all the natural numbers till x. Right? If we have n factorial, then we need to multiply all the natural numbers till n. So that is the meaning of factorial, and it is denoted by n and an exclamation mark or something like this. This is also not used, but we normally prefer with n and an exclamation mark. So that is the expansion of sin x, x upon 1 factorial minus x cube upon 3 factorial, and so on. Similarly, we have a cos x, which is x to the power 0, which is 1, and and to be noted, the 0 factorial is equal to 1. Right? We will prove it obviously, but in some other lecture, in another different topic called permutation and combination, we'll surely discuss about it. It's a very nice concept to learn, and obviously a very nice concept to derive to. So we look at cos x expansion, that is 1 minus x square upon 2 factorial plus x to the power 4 upon 4 factorial, and so on. You will notice that what is the power of x is the number in the factorial representation in the denominator. Similarly is the case with sin x. Also, one thing to note is that in sin x we have alternate negative and positive terms, but we do also have the odd numbers in the denominator and in the power, where in the cos x we have even numbers in the denominator and the powers, which is a very which is a very good tip for learning these expansions. Well, obviously we do not need to learn all this expansion. These are just, we just need to give a look to it so that we can get to our different results about using these. Right. Now next is the exponential function of e to the power x, which is a very important expansion, and it can be easily understood too. Well, it is 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial, and so on. So it's just a basic series in which I can say that if well, this here is written wrong. It's actually let me write it here, sigma x to the power n over n factorial, right? And where n starts from 0 to infinity. Right? If you don't know the notation, let me just explain you notation. The sigma symbol, which is a Greek symbol for s, stands for the summation. Like we try to combine all these sum terms into one thing and then denote the sigma symbol, which stands for summation. And n equal to 0 if the lower limit till the upper limit. The upper limit is infinity, the lower limit is 0. Like we need to put the values n equal to 0 and end it till infinity and add the whatever resultant terms comes to us. Like we try n equal to 0, we first make that term, and then we add n equal to 1, a term of n equal to 1, and so on. So that is the summation representation of e to the power x. Similarly, we have of ln of 1 plus x, in which the first part is more important than the second one. In this expansion is x minus x square upon 2 plus x cube upon 3 minus x to the power 4 upon 4, and so on. So that is a very basic term which does not contain any factorial representation, but it is very important though. Obviously, you do not need to learn the second part because it will be of no need to us, but it's just an kind of interesting fact that it somehow comes out to be in a recurring fraction type thing, and we'll go through these derivation once in a fact or something. The most important expansion of all this is the binomial theorem. Well, if you've heard about binomial theorem, you must know that it is the general formula of expansion of a binomial to the power n, like x plus a to the power n or x minus a to the power n. We all know that the expansion of x plus a whole square is x square plus a square plus 2xa, which normally comes by multiplying x plus a into x plus a, and thus we get it. Well, we can also get the same by using binomial theorem, and it has been got from binomial theorem only. So we get x to the power, I'm not written it completely, I write it with you. This x plus a to the power n is equal to x to the power n plus nc1 x to the power n minus 1 a plus nc2 x to the power n minus 2 a square, and so on till we have ncn a to the power n. You should note that before x to the power n we have an nc0. Now what is nc0? Well, nc0 stands for, like if I have ncr, it stands for the combinatorial argument of ncr, which means I need to select r objects out of n. Physically it stands for selecting r objects out of n, and it stands for n factorial over r factorial into n minus r factorial. So that is NCR, and we'll see that how it comes out to be in the chapter permutation and combination, but it's seriously very important. You should note that if we put r equal to 0, we'll get n factorial upon 0 factorial into n factorial, where n factorial and n factorial will get cancelled, and it will remain 1 upon 0 factorial, which is 1. So that's why I didn't write nc0, and similarly is the case with n minus ncn, and you can put the formula and check it out what it happens. Now let's move on. We have 4 limits here which we need to discuss today. First is sin x upon x. Well, we all know that sin x, using this formula here, sin x, we have x upon 1 factorial upon x cube upon 3 factorial and so on, which is discussed orally. Well, if I divide here by x, I'll get here 1 minus x square and so on, right? Now what do we have it here? We have limit x approaches 0. So that means that we need to put all x equal to 0 in that formula, and we know that we have 1 minus x square upon 3 factorial and so on, and the rest of the terms is all contains x. So now because x is so small that x square is smaller than that, I can neglect that term and we can cancel them out. We can cancel all the terms out, and thus it comes out to be 1. So we need to just know the sin x upon x limit x approaches 0 is equal to 1. This can also be derived from another rule or theorem which is called, or the law, which is called the sandwich theorem, and it's kind of a level 2 thing. We'll discuss it too, and it's not a fact, but it's a really helpful thing because we can calculate a lot of things about that. Then we have 1 minus cos x upon x. We can also, using the infinite series, we have that it is 1 minus x square upon 2 factorial. So similarly, if I put 1 minus here, then 1 gets cancelled, and these negative terms change to positive, and when I divide it by x, I get x upon 2 factorial and so on. So I get here 1 minus cos x upon x is equal to 0. The limit comes out to be 0 when I put x equal to 0. Now what about 1 minus x upon x square? Let's go back to here, and I just divide it by x square. Right, I do 1 minus cos x, this thing become positive, this thing become negative and so on. When I divide x square, these things become 1, right, and these become x square and so on. So what happens is this thing remains and the terms have contained x. So the limit when I put x equal to 0 will come out to be half. So this limit here is equal to half. Now the last limit we need to discuss is tan x upon x, which is similar to the first one, which is sin x upon x. I do one thing, I write it as sin x limit x approaches 0 sin x over x into cos x. Now there is a small rule about product rule in limits, in which I can say that limit if x approaches 0 f of x into g of x is equal to limit x approaches 0 f of x into limit x approaches 0 g of x. This is called the product rule in limits. We will learn about some more rules about addition and product, so we can apply it here, and I'll get cos x, limit x approaches 0 cos x, and limit x approaches 0 sin x upon x, which we have calculated in the first one, and which is equal to 1. Obviously, when I put x equals 0 here on cos x, I'll get 1 into 1, which is equal to 1. So that is another thing, and it can be similarly calculated with the help of sandwich theorem. So these were the main things which I needed to discuss. We'll discuss these next two limits in the next class. I'll let you try these two limits and use infinite series for that. And if you somehow know L'Hopital rule, please do not use that. Plus try to use infinite series. And if you can just send me the solution that you have. Let's see who does that first. So that's it. Try these two questions and do revise it from any book of your choice.